All right, let's try that again. I messed up in the original video, so I'm re-recording as a separate example problem. So we're gonna try an example problem looking at combustion. All right, so example for chapter 15, combustion. Beefy, please keep it down. All right, so we have 1 kilomole of octane, 1 kilomole of octane, octane being a hydrocarbon fuel, or given its chemical formula is C8H18, 8 carbons, octane. You'll learn, you should learn about that in fundies if you haven't already learned about it in Chem 1 or Chem 2. Nomenclature of organic compounds. All right, so 1 kilomole of octane is burned with air. It's important, it's air, it's not oxygen, it's air, which is only about 21% oxygen. That contains 20 kilomoles of O2. Beefy. Okay, assume the products are carbon dioxide, water, oxygen, and nitrogen. Assume the products are CO2, H2O, O2, and N2. Okay. Determine the mole number of each gas in the products and the air to fuel ratio. Determine mole number of each gas of the products and the air to fuel ratio. Okay, so we have some sort of situation that looks like this. We have a combustion engine or chamber, and we know that our products here are CO2, H2O, O2, and N2. We know that incoming, we have 1 kilomole of octane and 20 kilomoles of O2, which are in air, which means that only 20% of air is 20 kilomoles of oxygen. Okay, and then we have these products, and we want to determine the mole number of each of these products. So I'm just gonna put in a filler here. I'll do A, B, C, and D. And we're gonna solve for A, B, C, and D, and then we're gonna solve for the air to fuel ratio. All right, so generally for this reaction, we're gonna have 1 kilomole of C8H12 plus 20 kilomole of O2 in air. So we're gonna have more than just oxygen here. We're gonna have a lot of nitrogen, which is important for balancing our products. And then these are going to go to an A amount of carbon dioxide, a B amount of water, a C amount of oxygen, and a D amount of N2. Make sure you write your A, B, C, and D very separate because you don't want this to look like CO2. All right, now I wanna look here at air. We know that air is about 79% nitrogen and 21% oxygen. So these are N2 and O2 actually, but we're gonna just say like 79% of air is nitrogen, 21% is oxygen, and we have 10% that is other. So this is composed of, you know, a little bit of argon, a little bit of carbon dioxide, and we're gonna say that these are pretty irrelevant for these products here because they're gonna appear in such small quantities. So we're really only looking at nitrogen to oxygen. So we have 0.79 nitrogen to 0.12 oxygen, which gives us a ratio of 3.76. So this is saying for every 1 oxygen we have 3.76 nitrogen. So for every 1 O2, we have 3.76 of N2. Okay, this allows us to plug in to our equation here. So we have 1 CH18, 1 kilomole plus 20 kilomoles of O2 plus 3.76 N2, assuming that there's a 1 here. This goes to A CO2 plus BH2O plus CO2 plus DN2. All right, so now we just want to balance the equation to figure out what A, B, C, and D are. You've probably learned several methods of doing this in Chem 1, Chem 2. The book and some online resources use kind of algebra-based methods, so that's what I'm going to do here. First, we write down all of our quantities on the reactant side. So we have carbon, hydrogen, oxygen, and nitrogen. On this side, we have carbon, hydrogen, oxygen, and nitrogen. All right, so we have how many carbons? 8. We have how many hydrogens? 18. How many oxygens? We have 20 of O2, which is going to be 40. And then nitrogens, we have 20 of N2 times 3.76. So 20 times 2 is 40, times 3.76 is going to be 150.4. And then for our products, we are going to find A, B, C, and D. So I'm going to start with the values that they're only appearing in one of the products. So carbon only appears once, hydrogen only appears once, and nitrogen only appears once. So for carbon, we have A times 1. So 1A equals 8. That means that A equals 8. For hydrogen, we have 2 of B. So 2B equals 18. This is the only place hydrogen occurs. So B equals 18. For oxygen, this is the one that occurs in 3 out of the 4 products, so I'm going to skip that one for now. For nitrogen, I have 2D. 2D equals 150.4. So this D is going to be equal to 75.2. So for oxygen, for C, we know that we have 2C, but then we also have 1B and then 2A. But here I know that my A value is already 8 and my V value is 18. Oh, I'm sorry, my B value is 9 because I didn't divide by 2. All right, so this gives me, and these are all equal to 40. So this gives me 2C plus 9 plus 2 times 8 is equal to 40. So 9 plus 16 is 25. 40 minus 25 is 15. So this gives me 15 equals 2C. Dividing by 2, C is equal to 7.5. So now I have A is equal to 8, B is equal to 9, C is equal to 7.5, and D is equal to 75.2. So now I can write this equation. I have 1 CH18 plus 20 O2 plus 3.76 N2 goes to 8 CO2 plus 9 H2O plus 7.5 O2 plus 75.2 N2. All right, so here is our equation of this combustion reaction. As a note, this method of balancing equation only works if you know for sure your concentrations of your reactants. So if this side of the equation is not balanced, you can't write your reactions like this, your reactants like this, like they're fact. All right, so we've solved for the mole number of each gas of the product. So now we just want to solve for the air to fuel ratio. So air to fuel ratio is equal to the mass of air over the mass of fuel. And in order to figure out the mass of air, we can use table A1 in the back of the book. Table A1 to figure out the mass of air. Table A1 is on page 898. We've used it before, especially looking at these critical point properties. But table A1, air, our molar mass is 28.97 kilograms per kilomole. I'm going to say 29 kilograms per kilomole. So here our mass of air is 29 kilograms per kilomole. All right. And for air here, we're saying that for every 1 mole of air, we have 1 plus 3.76, 4.76 moles of oxygen and nitrogen. So this is kind of a confusing concept. Okay, so we know the molar mass of air, but in order for us to get to mass, which would be kilogram, we need to multiply by kilomoles. So we know that we have 20 kilomoles of oxygen in this problem. That's what we're told. But for every 20 kilomoles of oxygen, we have 20 times 3.76 kilomoles of nitrogen. So in order to account for our oxygen and nitrogen in air, so here we're looking at air, we need to account for both nitrogen and oxygen. So for this equation, we're not going to use just 1 or 3.76 or 20. We're going to use 1 plus 3.76, which is going to be for every mole of air, we're going to have 1 oxygen, 3.76 of nitrogen. So this is going to be all right, so here I know that I have 20 kilomoles of air. So I have 20 kilomoles of 3.76 plus 1, 4.76 moles of air. So here's my air. So I looked up my molar mass in the back of the book in table A1, and then I was given 20 kilomoles of oxygen, but I know for every 20 kilomoles of oxygen, I have a total of 4.76 of air because of this oxygen only being 20%. All right, so then my mass of the fuel is a little more straightforward. My fuel is just my hydrocarbon here. So I know I have 1 kilomole of this starting hydrocarbon, but this breaks up into my carbon and hydrogen. So there's no carbon or hydrogen here, there's no carbon or hydrogen here. So the mass of my fuel is going to be 12 kilograms per kilomole, which is carbon, right? So that's the mass of carbon. And my carbon, I have 8 kilomoles based on my value for A. And then for hydrogen, hydrogen has a weight of 2 kilograms per kilomole. This is for hydrogen. And I have 9 hydrogen kilomoles here. So if we plug in these values, we get about 24 kilograms of air per kilogram of fuel equals 24 kilogram air per kilogram of fuel. Sorry, that got a little winky there all. 24 kilograms air to kilograms fuel. Okay, so this air to fuel ratio is explained a little bit more on page 746 and how they solved it here. They provide a little bit of explanation of where the values come from, but you're looking at the mass of air over the mass of fuel. And in order to get the mass of air, you need the weight of air, which we looked up in table A1, and you need to multiply it by the amount of air that was there. So we know that the amount of air is 1 oxygen plus 3.76 nitrogen times by the amount of kilomoles. So 20 times 1 plus 3.76 times the weight of air. Then we're looking at our carbon species and our hydrogen species, multiplying those by their respective weights, getting the ratio that we want here. Okay, so that's all that I want you to know from chapter 6, just basic combustion, making sure you can balance equations and you feel comfortable working with carbon, hydrogen, oxygen, and nitrogen species. These are kind of the most common elements that we're gonna be looking at for the rest of chapter 15 and 16 roughly, more like all of chemical thermodynamics. All right, have a great day.